Hello everyone, I'm Darshini Mahendran. Today I'm here to describe our team's participation in the shared task of CLEF 2020 challenge in information extraction. This is the outline of today's presentation. ChemU proposes two key information extraction tasks over chemical reactions from patent documents. Our team participated in both task 1 and task 2. Task 1 aims to create systems to perform named entity recognition over chemical patents as the first step in chemical reaction detection. The task 2 aims to create systems to perform event extraction over the entities to identify the individual steps in the reaction. The table here shows the event statistics of the training dataset. ARG1 event label corresponds to the relations between a trigger word and chemical compound entities. And ARG-M event label corresponds to the relations between a trigger word and temperature, time, or yield entities. First, I'll explain the system we built for task 1. To identify the experimental parameters and triggers from the data, we use bidirectional long-short-term memory LSTM units with conditional random field CRF output layer implemented in PyTorch. LSTMs are a type of RNN. They have two sources of input, their current state and their past states. This allows them to connect to the previous observations, such as words in a sentence, and learn dependencies of these words over long distances. In bidirectional LSTMs, data is presented in both directions and with two separate hidden layers and then fed forward into the same output layer. This allows the system to exploit context in both directions. A linear chain CRF is used to assign the final class probability, and the CRFs are a sequence learning algorithm which incorporate the interdependency between labels into the model prediction. Therefore, using a CRF output allows the model to use the preceding label predictions to inform what labels are most likely to follow or to occur closer. The input to our BioSTM CRF model is the work that is in this work is pre-trained word embeddings and character embeddings. These embeddings are concatenated and passed through the network. The figure here shows a simple example for the term mice. The network is valuable for providing input, especially in the case of out-of-vocabulary words. Now I'll explain the system for task 2. To identify the trigger words, we used our NER system as described previously. And to identify the chemical arguments between the trigger words and the entities, we use a Python-based relation extraction framework. The framework contains two main components, rule-based method and convolutional neural network-based method. First is the rule-based method, which utilizes the co-location information of the trigger words to decide that with respect to the entity, if the word is referring to a trigger word or not. So we use a graph-based algorithm to find the closest occurrence of the triggered word. For each entity in the dataset, we traverse both sides until the closest occurrence of the trigger word is found, using the provided span values of the entities. We applied the following traversal techniques and determined the most efficient traversal technique for this task. Here, we used left-only traversal, where we traverse to the left side of the entity and find the closest occurrence of the trigger words. For example, if we look at the sentence, both trigger words can have relations with solvent. But the solvent has a relation with the closest event trigger added, but not with the event trigger still. This is correctly captured by the left-only traversal. Next is the CNN-based method, which extracts and classifies the events automatically. The convolutional neural networks are a form of deep neural networks and mostly consist of four main layers: embedding layer, convolution, and pooling and feedforward layers. The figure here shows an abstract view of the construction of the CNN-based model. For each trigger word entity pair, we perform a binary classification to identify whether there is a relation between the trigger word and the entity or not. First, we identify and extract the sentence where the trigger word entity pair lies, and based on where the pair is, we break the sentence into 5 segments. Preceding segment that has the tokenized word before the concept. Concept 1 segment, it has the words of the first concept. Middle segment has the tokenized words in between the two concepts. And concept 2 has the words in the second concept. And the succeeding segment has the words after the second concept. Here we use the chem-pattern pre-trained word embeddings. We construct separate convolution units for each segment and concatenate before the fixed length vector is fed into the dense layer that performs the classification. Each convolution unit applies a sliding window that processes the segment and feeds the output to the max pooling layer to extract important features independent of their location. Finally, the softmax layer performs binary classification. Next, we'll go to the results and analysis. These are the evaluation matrix we use to evaluate our systems on. First, I'll present the results of task 1 for each runs individually. Tables show the exact and relaxed precision recall and F1 scores obtained over the test data in each of our 3 runs. Overall, the BioLSTM CRF model trained using chem-pattern embeddings returned the best results, obtaining a 96.7 system-wide relaxed F1 score. This model performed better than the baseline for all entity labels except example label. This model's performance is likely due to the domain-relevant information contained within the embeddings. Model for run 2 was trained over the training data using the BioLSTM CRF with the WikiPubMed embeddings. This run's results is almost similar to the previous results. Run 3 model was trained over the training and development data combined with BioLSTM plus CRF using the WikiPubMed embeddings. This model's overall performance was lower than the baseline model, but the best performance for exact evaluation resulted from this model. We believe this may be due to the increase of volume of data used to train by the addition of the development set. Now I'll go into the results of the task 2. Run 1 shows the system results of the CNN-based model. This obtains a higher overall F1 score than both the rule-based models. When training with CNN, the overall precision of the predictions is high, but the recall is low. This shows that CNN failed to classify all instances, but was able to classify most of the predicted instances correct. Also, we can see the performance of each event class, trigger word entity pair in run 1 is proportional to the number of instances in the training set. For example, event classes reaction step reagent catalyst and reaction step starting material have more training instances and obtain a high F1 score, whereas the event class workup solvent and workup starting material have a very few instances and obtain an F1 score of 0. Run 2 and 3 are rule-based models. Here, the trigger words were identified using the NER system trained with ChemU pattern embeddings. These models obtain comparatively high recall and lower precision. And rule-based methods predict all the closest occurrence of the trigger words. However, many predictions are false positive. Since the number of instances in the training set does not affect the rule-based methods, the performance of the event classes that have few instances performs better. For example, the event classes workup time and reaction step other compound obtain 0 F1 score with CNN-based model, but performed better with the rule-based models, obtaining F1 scores of 0.43 and 0.88 respectively. This is another rule-based model results. The difference in the trigger words identified using NER system were trained with Wikipubmed embeddings. This shows similar performance to the previous rule-based method. This table here shows the arithmetic and weighted arithmetic mean of the precision recall and F1 score for both trigger word classes for each run. We can see the CNN-based method performs well with the reaction step classes and poor with workup classes. This is because most of the reaction step classes have more instances for the CNN to train on, and most of the workup classes have few instances. This is the same reason the rule-based methods perform better with those classes. The weighted arithmetic mean results contradict with the arithmetic mean result. As we can see, a notable difference in the F1 score when comparing the classes of reaction step and workup. The workup event class obtains a better performance due to the significant imbalance between the individual event class. The weighted arithmetic mean allocates more weight to the classes that have more instances, and vice versa. We see an improvement in the performance of both classes. For task 1, although the exact results for the models perform slightly worse than the baseline, each of the models perform better on the relaxed results. This discrepancy may be due to the way that NER system handles entity classification. But for task 2, table shows the comparison with the co-occurrence baseline and the overall results from each of our runs. The results show that all 3 runs obtained a higher precision and F1 score than the baseline, but not recall. The system results show that the CNN-based model obtains a higher overall F1 score than both rule-based models. So these are the conclusions for the task 1. We evaluated 3 bilistian CRF models over different pre-trained word embeddings, and models did not outperform the baseline model when evaluating the exact span matches, but models outperformed the baseline when evaluating in relaxed modes. Errors primarily occurred because of these issues with the model distinguishing between different entity levels. These are the conclusions for task 2. We used a CNN-based model and 2 rule-based models to extract events. All 3 models outperformed the baseline model. CNN-based model outperformed the rule-based model, especially with the reaction step classes, as those classes have more instances to train on. Rule-based methods do not require training instances to train. They perform better with workup classes. So in future, we are planning to explore additional segment CNN architectures and different feature representations. Thank you.